Today we're going to be looking at resonance in tubes. Now in class we only talked about resonance on a string, right? We talked about resonance on a string. What kind of wave, what do we call the kind of wave you set up when you have resonance on a string? A standing wave. Okay, and the standing wave for the string had a boundary condition that each side had to be not moving. And what do we call the position on a standing wave that are not moving? Nodes. So for a string, we had nodes on each end, and that gave us conditions that the wavelengths that would resonate on that string had to have wavelength that resonates is equal to, I believe it was 2L over N, where N was any positive integer. Obviously, N can't be zero because you'd have a division by zero error. And it can't be negative because you can't have negative wavelengths. But we had, those were the wavelengths that would resonate. Now, for lab today, we're going to we're going to be exploring tubes that resonate. So you have two types of tubes that can resonate. And I'm actually going to go to the textbook, maybe. The textbook supplement on this topic. Harmonic series in tubes. And we have two kinds of tubes we talk about, open tubes or closed tubes. An open tube is a tube that's open on both ends as shown here. Now, if it's open on both ends, you're going to have the same condition on both sides, right? Because it's open. Well, what do we talk about to describe a sound wave? There's two answers to this, two correct answers. What do we talk about to talk about a sound wave? What is the very thing that's varying? Okay, I heard pressure and the other one? Displacement. The two options are pressure or displacement. So we're going to look at the boundary condition for both of those to begin with. If I have an open end, what's the pressure going to be at the open end of a tube? So open end of a tube would be like, here's an organ pipe. It's open here. So what's the pressure going to be here where it's open? Atmospheric pressure. So it's going to be a constant atmospheric pressure here. Now this tube also is open here where the whistle is open. So this is open on both sides. This is a standard open tube. And so the pressure is going to be constant on both sides. So our boundary condition in terms of a standing wave, what is it going to be if the pressure is constant? The words are node or antinode. Okay, so it would be a pressure node on both ends for an open tube. And so that's what's shown in these pictures. So the top picture has, it's open on both sides and the pressure can go anywhere between maximum above atmosphere and maximum below atmosphere. So the green line on the left side is showing maximum above and on the right side maximum below. The orange line, maximum below on the left and maximum above on the right. The next one below, notice you have more than half wavelength in the tube, but it's going to be the same condition as a wave on a string because you have a node on both sides. Just like for a wave on a string, you had a node on both sides. So if you have an open tube and you're looking at the pressure, it's a node on both sides, which requires then that the wavelengths that will resonate here are going to be 2 times the length divided by n, where n is a counting integer, exactly like a wave on a string. But there's the displacement idea. Displacement is the motion of the molecules. If I have an open end like this, can the molecules move at the open end? Yes, they can. So the molecules will definitely not have a displacement node because they can be moving in and out. And it turns out because it's an open end, it's going to be a displacement antinode for the motion. Yeah, I explained this picture all wrong. That is actually showing displacement. I don't know what I was thinking. I said pressure going high and low at the ends. The pressure was nodes. It's the displacement that can go high and low at the ends. I wish I could back up. I should, but I won't edit that out for the evening lab over at Southwestern because that was a mistake. This was showing, and I sadly can't write on this, but it was showing displacement is what the graphs were, not pressure. Let me go back to where I can draw and draw in what those should look like. So if I have a tube and I'm looking at displacement, the displacement is going to be an antinode at both ends. And so the displacement can go like this. That was horrible. Erase. I'll put it inside as it was shown there. It can go like this, or it could have more waves in there, so it could go like that, but it has to have an antinode at both sides. If we look at pressure instead of displacement, the pressure has to be on node at both ends. So the pressure can go like that or like that. Now, a question that's easy to miss. What can you tell me is going on with the pressure right here? What's the pressure doing? Let's say we're in the blue one, so I chose a place where we are at an antinode for the pressure. What's the pressure doing at that antinode? Is it staying constant? No. So it's not staying up here at the top and it's not staying down here at the bottom. Instead, the pressure at that point is ranging between. So sometimes the pressure will be a maximum, sometimes it'll be a minimum, sometimes it will be zero because it's going all through the range. Whereas if I come out here, the pressure is staying constant. So whether you look at the displacement picture or the pressure picture, you still have the relationship that says the wavelengths that will resonate is 2 times the length divided by n, where n is a positive integer. So that's for open tubes, such as this. Beautiful. Okay. What about closed tubes? What's the difference in an open tube and a closed tube? A closed tube is closed on one side, not both sides. If it was closed at both ends, then it would be at best a drum, not a wind instrument. So for wind instruments, it has to be open on one side for sound to come out. So I can close this on one side and blow on it. It's only a high pitch I can get out of this when I have one side closed. This is a bad example for that. This one's easier. Notice by blowing harder or softer, I get different pitches. The lowest one is what we call the fundamental. That's the one where the wavelength is 2 times the length. If I blow a little harder, then we're getting the first overtone, because it's the first frequency above the fundamental, or the second harmonic because it's 2 times the fundamental. And that's the one where one wavelength is fitting in here. Now I'm going to put my hand over the bottom. I can't get the lowest note with my hand over the bottom, same problem I was having with that one, but I can get a higher one. Notice this is not the same as what I get without my hand, so listen. It's between those two. So you get different pitches when you put the end covered versus when it's uncovered. Why is that? It's actually pretty simple. If I have the end covered, so if I have now a tube that goes like this, we call this a closed tube. My brain goes many letters ahead of what I'm writing. A closed tube, because it's closed at one end, the pressure at this side is going to be a pressure. What did we say the pressure is going to be at the open side? It's going to be atmosphere. It's going to be a pressure node. At the other side, we have a solid barrier. I can push in that barrier as hard as I want. There's no restriction on the pressures there. And so just like displacement at an open end, the displacement could be anything, and it turned out it was an antinode. The pressure at a closed end is an antinode. Now, if instead of talking about pressure, I changed to talking about displacement, the opened end was a displacement antinode. The closed end, what can you tell me about the velocity of a particle when it hits the end? It's going to stop and not go any further, right? So particles there at the end, they have to stop, which means that that's going to be a displacement node. So for the closed tube, one side, whether you're looking at displacement or pressure, one side's a node, one side's an antinode. If I draw the pictures in green, I'll write the displacement. So the displacement was an antinode going to a node. So there is the fundamental looking at displacement. If I look at pressure, which I'm actually going to draw in blue, it's just the opposite. How many wavelengths fit in this tube? That's a quarter wavelength. So with the picture I have right now, I have the length is equal to 1/4 of a wavelength. Now, if I want to go to the next resonance, the next standing wave possible, I will have to go to the picture shown in the second tube here. It still has, in this case, it's showing me the displacement. So it has a displacement node on the closed end, a displacement antinode in the open end, but how many wavelengths do you go to go from the next node to antinode? That's 3/4. And so it turns out that in general, I have the lengths are equal to n/4 wavelength, where n is only odd numbers, 1/4, 3/4, 5/4. Or solving that for wavelength like we did up above, the wavelengths that will resonate are equal to 4L over n, where n is the odd integers. So we call this an odd function because it only works with odd integers. So the closed tube only plays odd integers. Now, how did we go from wavelength to frequency in class yesterday? Frequency equaled a simple relationship between wavelength and speed. What's that? It's the speed divided by the wavelength. So that's going to be the speed of sound in air, because we're talking about sound in an air column, divided by, and if it's a closed tube, that would be 4L over n. And so this here is our fundamental frequency. Fundamental frequency is speed of sound in air divided by 4L if it's a closed tube. If it was an open tube, it would have been the same as we found for the string. So for the open tube, it was V over 2L multiplied by N. So my fundamental frequency is V over 2L. The closed tube has 1/4 V over L. The open tube, 1/2 V over L. So the fundamental is 1/2. You play a lower fundamental with a closed tube than you do with the same open tube. One thing that's really interesting to note, though, is if you go from one harmonic to the next harmonic, that is if n goes from, let's say, 7 to 8. If n goes from 7 to 8, how much does your frequency go up if you have an open tube? What's that equal to? n plus 1 times v over 2L minus n times v over 2L. It's just v over 2L. So the difference between adjacent frequencies with an open tube or with the wave on a string is equal to the fundamental. If we go down to the closed tube, because it only plays odd numbers, you have to go up by 2 for adjacent frequencies. And so it would be n plus 2 times v over 4L minus n times v over 4L, which is equal to, okay, 2v over 4L, or more simply, v over 2L. Look at that. The change in frequency is the same amount if you have an open tube or a closed tube. But the fundamental is not the change in frequency if you have a closed tube. How does the fundamental relate to that frequency difference if it's a closed tube? It's 1/2 of it, right? And notice the closed tube, if you continued going down by that change, it wouldn't stop at 0. It'd go past 0. So that's the difference in an open tube and a closed tube and the resonance conditions. So in our lab today, we're going to be looking at these resonance conditions. So let's shift to the instructions. This is kind of out of place, but let's watch this YouTube video on resonance because it's totally cool. I don't think we're going to have any sound, but that's, at least we don't have to turn down the sound. So what this is going to do is show a plate that has sand on it, and then you just have it connected to a speaker to shake it. And look what's happened here. You have the sand that's moved to specific locations on that plate. Why, in terms of a standing wave, what would the positions be where the sand congregates? There'd be nodes, places where it's not moving. So on this two-dimensional plate, the standing waves are a little more complicated than what we saw for a wave on a string. That one-dimensional situation is simple. Two-dimensional is harder. Three-dimensional, well, yes, much harder. So this here is a standing wave. So it resonates at this because it's setting up a standing wave. You can tell it's setting a standing wave because you have positions with nodes. So now they're going to raise the frequency. And as you raise the frequency, you see, it's broken apart. And it looks pretty much the same, right? Raise it some more, please. Okay, so he raises the frequency, and you see that it's not quite there yet, but it's going to form another standing wave that looks now significantly different from the last one. And as he keeps going up in frequency, he will go through a large, actually she, I'm pretty sure that's a she's hand. It's going to go through a lot of different variations of standing waves on this two-dimensional shape. Now, if you think about with Jordan and his cello, it resonates quite well at just about any note inside that chamber because it's a very complicated shape and there's always going to be some dimension where you can get resonance for almost any frequency. And so that's part of the design of that so you can have sound resonate in the resonating chamber. One of my friends is an opera singer, and when she was in graduate school, her professor kept telling her she had to grow her instrument. Now, if you're a singer, what does it mean to grow your instrument? You're not going to make yourself grow taller. You're going to make yourself grow bigger. Apparently, she said that her professor was a large woman who definitely believed in the old adage about the fat lady singing at the opera, and she wanted her to increase the size of her body. What theoretical reason would there be for that? You're going to change the resonant behavior of your body by changing the weight you carry. And her teacher believed that the more weight she carried, the better she would resonate, the better her tonal quality would be. Okay, I'm going to stop with this. You can watch the whole thing. If you listen to it with sound, it'll just, bust your eardrums or something. So here is the first half of today's experiment. The first half is the prescribed part, the part that everyone has to do. we have a closed tube. What is that closed tube? That closed tube consists of two tubes, one inside the other. We're going to fill this with water. So, of course, I make a mess. We're supposed to have these things here to keep us from getting water all over the floor and keep people from falling and hurting themselves. This is the genius way of doing it, not. You can see the knot part there. Okay. I'm sure there's a faster way of doing this, but it's filling. Obviously, if I turn the water pressure up, I just spray water everywhere.
You found it at a weird angle so that it can't reach the water.
I realize that. But there's really no option.
Pointing it towards you, because there's less.
There might be a little less. But we're almost done here. Okay. So I filled it with water. Now the length of my tube is going to be from the top of this inside tube down to the water level. And we're going to measure the conditions where resonance occurs. So we're going to get, is there a rubber stopper there? Excellent. Actually, got that. Come on up and help me out. The rubber stopper here is to bang your tuning fork on. We don't want to bang the tuning forks on hard things because it's not good for the tuning fork. It makes them eventually play bad notes. So go ahead and hold this. I'm going to take the tuning fork, hit it on my stopper. My leg's still bend barely. I'm going to listen to it with my ear. Can you tell it's resonating? Right, it's definitely louder when it's resonating. So what I'm going to do is find the length when it resonates. And I can tell my partner there, and he's going to grab it with his hand up here. So when I say there, he can just put his finger on it and hold it in place. Just one hand, like that. So he can hold it in one place and hold that position. Then I grab my meter stick, and goodness, the meter sticks have been borrowed or something because there's not that many left in the classroom. I would have to throw it, but something disastrous would happen. And now, while he's holding it, I'm going to measure with my meter stick the distance from the water level to the top of the tube. Now keep in mind, as you raise the tube, the water level drops. So you can't just hold the meter stick the same place and measure every time. You have to move it to get the water. So I'm going to measure this distance. So that's, to the best of my measurements, without being careful at all, 7 centimeters. You should have more, at least have tenths of centimeters. You can't get much better than tenths of centimeters because, remember our first lab estimating error, I'm trying to read sighting over to where the water level is. There's a lot of uncertainty in how I'm reading that. So I can't get better than a tenth of a centimeter on here, a millimeter. So we found the first one, then we go up to the next one, first one, second one. So I'd have him hold it there, I'd measure the height, then go to the third one, and keep going and do all of the frequencies that you can, or not frequencies, but all the lengths you can find where it resonates until the bottom of the tube comes out of the water. Once the bottom of the tube's out of the water, you're done, right? Because you no longer can really control the length of the tube. Air can go up on the outside, and it's no longer your nice closed tube situation. So you're going to measure each length where you have resonance for your tube. Remember, don't hit the tuning forks on hard things. Just put it somewhere where it won't fall over. So that's the measurement you're going to do. Now, how are we going to analyze that? According to what we've just gone over, the lengths that resonate for a given wavelength, notice in this case we had changing length and a constant wavelength. So it's L sub n instead of lambda sub n. The lengths that resonate for a given wavelength are odd multiples of lambda over 4. So you can right away, if you find your first one, you can guesstimate what the length should be for your next one, because if the first one's 1/4 wavelength, what should the next one be? 3/4 wavelength. So you take that number, multiply it by roughly 3, and that should be about where you are. If you miss the first one, you'll be able to tell because, whoops, that doesn't roughly follow the pattern. Now, it's not going to be exact. So you record all of them you can using the same equation that we just used a minute ago to relate wavelength, speed, and frequency. We can put the lengths in terms of the frequency and the speed, or we could solve for the speed of sound. The speed of sound in air depends on the temperature of the air. I told you in class that the speed of sound in air is not the speed of the molecules in the air, but it is related to it. And so it depends on temperature, and I have two equations here. One equation in the red box, one equation almost in the blue box. There we go. You can use either one of those to convert from temperature into speed of sound. How do you get the temperature? You come on up here and you say it's 69.6 degrees Fahrenheit. And then you take it from Fahrenheit and you have to convert it to Celsius to use this equation. And then you calculate what the speed of sound in air is. You're going to compare your experimental speed of sound from your measurements to the theoretical speed of sound in air you get from that measurement. So how do you find the experimental speed of sound? Well, you just find the wavelength. The frequency is stamped on your tuning fork. So in your data table, you should have frequency and, the one Rachel's holding, what does it say? 1024? 512. Okay, so she has one that says 512 hertz. And then she's going to find the lengths that resonate. The best way to find the wavelength is to make a graph. Why make a graph? Well, one thing I told you wasn't exactly correct. I said the open end of a tube was a pressure node. It turns out the pressure node is not right at the end of the tube. It's a little bit farther out. That distance out has to do with the diameter of the tube. And so we call that the end effect. So it's actually the effective length, which is the length you measure. The Ln is the measured length. Measured starts with an M. Plus that end effect length. So since the measured thing is what we measured, I take this equation that says the effective length is N times V over 4F, and just solve it for L sub N, the measured length. And that measured length is going to give me this equation. So if I make a graph and I put the measured length on the y-axis, and I put this integer n on the x-axis, what should the slope of that line be? It should be just 1/4 the wavelength. So if you make a graph, and that's what you should do, of the measured length on the vertical axis and n, so n will be 135 as far as you got on the horizontal axis, then the slope should equal wavelength over 4. Therefore, the wavelength should be 4 times the slope. And notice you can read from the y-intercept what the end effect was. So you need to determine what the end effect was for your experiment with your tuning fork and what the wavelength is. And then once you have the wavelength, you're just going to use, back to this equation, the speed of sound is equal to wavelength multiplied by frequency to find your experimental speed of sound to compare with the theoretical speed of sound that you got from this one here. So each person, so if you have a group of 2, each person in the group will have to choose a tuning fork with a different frequency. You don't want 2 people in the same group to have the same frequency tuning fork. And measure all of the possible lengths where it will resonate, find the end effect and the wavelength, and from that wavelength and the stamped frequency, find the speed of sound and compare to the theoretical. Then you have the part that you're doing to test the theory. So what's the theory? The theory is the theory on open tubes and closed tubes. Now I'll actually just leave them on the screen when I'm done. I have a couple different websites that I located, these ones right here. They have information about specific things about the resonance of tubes. So let's look at these just so you can get an idea of what they are. So the first one, pipes and harmonics. The second one, clarinet and flute. And the last one, brass instruments. If you brought a brass instrument, obviously you'd want to look over the brass instrument one. If you brought a woodwind, the clarinet versus flute one. And then the first one, pipes and harmonics, is a basic thing that tells you some keys. So let's look at each of these. These are all from the same professor or somewhere in Australia. Yes. So pipes and harmonics is the first of these. The pipes, come on. The pipes and harmonics, first of all, lays out what I have talked about is exclusively for cylindrical pipes. The resonance for conical pipes is different. So I was happy to see that Aaron brought a clarinet, because a clarinet is essentially, forgot, can't write on this. A clarinet is essentially a cylinder, whereas an oboe is essentially a cone. And so the oboe and the clarinet actually have different resonance conditions because they have different shapes inside. The bores are different. The flute, how's the flute different? Well, everybody knows a flute doesn't have a reed, and a clarinet and an oboe have reeds. The flute has an open hole. So it's open on the end where you blow over, and it's open on the other end. It's open on both sides. It's an open tube. The clarinet, with that reed, the reed vibrates opening and slapping shut, and it behaves like a closed end of a tube. So the clarinet is a closed tube, like what we're doing for our experiments, whereas the flute's an open tube. And yeah, the oboe is a whole different ball game because of its conical bore. So you can read here about the differences that the bore makes for resonance. It's showing standing waves in a flute, in a clarinet, and then in the oboe, and shows some things about what the waveform looks like. If we go to the specific flute versus clarinet, you can see things where it's showing the pressure wave. When it's dark, going to the right here is dark. That is a pressure wave that's more compressed. When it's lighter, you can see there's a light thing going back. That's a rarefaction returning. And you can see the reflection going back and forth from the open ends. That's what's happening in the flute. The clarinet is behaving, come on, scroll. The clarinet is behaving like this picture that's now in the top part of the page, where it comes and reflects off the back. Okay, this one here, not a musical instrument. Just there for comparison. And then it goes through and talks about the frequency analysis. This is showing a harmonic. So the top one is showing n equals 2 for your flute. And you see you have a pressure wave and a rarefaction going back and forth against each other. The bottom one is for the clarinet, and that, you notice it doesn't have 2, it has 3. Why doesn't it have 2? Yeah, because it's closed, it doesn't have an n equals 2 option. It has n equals 1, n equals 3. So that's the next option, that's the next overtone. So this is the n equals 3 case. The final one here then is for brass instruments. Brass instruments, as you can tell from the menu, they get much more complicated. A brass instrument essentially has 3 parts. It has, okay, here we go. It has the mouthpiece with a conical opening. Then it has a tube with a constant cylindrical bore. And then it has a bell that's opening up again. And the conical parts change the resonance behavior so that a brass instrument, well, where does it show the pedal note here? Somewhere it's got a picture with the pedal note. Okay, maybe it wasn't here. I thought it was here. Anyway, the brass instruments have a very complicated system for resonance. And you can see here, like, the way you make it work is by going, and And it just sounds nasty, but what's happening is your lips are flapping open and closed and letting out bursts of air. And the mouthpiece makes it easier to control things. The back pressure makes it much easier. You have back pressure, and when that hits your lips, it helps your lips to close up. And so your lips and the resonating sound will work together so that you will only be making a large amount of sound with a frequency that will resonate through the instrument. So nobody in this classroom, I don't think, brought a brass instrument. But if you want to look at the brass instruments and how those play out, this is a good page for understanding that. So with your instruments, what are you going to do with your instrument? You know, what would I recommend for Erin? Well, one thing Erin can do is she can take her instrument and look at the frequencies it plays. Because when you play the clarinet, it's not going to play just one perfect pitch. It's going to play multiple pitches. And the clarinet, is it open tube or closed tube? It's a closed tube. So by theory, if it's a closed tube, what frequency should you see? Odd multiples of the fundamental. And so when she plays it, she can bring up Data Studio. Now, I don't even have this saved, but you just need to put the fast Fourier transform. If you look over on the right, you see where it says FFT right there. You put that FFT on there, and that's going to show you what frequencies you're playing. I also put the scope on there. That's the one right above FFT, so I can see the waveform. And then make sure you put it on fast monitor mode. See down there at the bottom, fast monitor mode. It will just stop after a short time if you don't put it on fast monitor mode because you'll have too much data. So put on fast monitor mode, and then you just click monitor to take data. And, well, let's just, instead of playing with the tube, let's play with my voice. I'm going to say, ah. So that's what ah looks like. Do you see a repeating unit there? Yeah, I have a repeating unit. That's the fundamental frequency. That's the pitch you identify for that ah. And then if you look over here, and something, you can mess around with the sampling rate, maybe. When you change the sampling rate, it will change the resolution there. But you can see the fundamental for my ah was there somewhere just below 200 hertz. And that's the pitch that you would hear for it. But that wasn't the strongest frequency. The strongest frequency was out here at about 610 hertz. But you don't say it's a 610 hertz note. You say that was, the 190-ish or whatever it was. And then you have the overtones. So let's just compare ah, e, oo, a, and o. So ah, e, oo, a, o. Now, they were all the same pitch, right? But the frequencies that made them together are distinctly different, especially if you go like E, ooh, E. Okay, come on. E, O, E, O. See the distinct shift? And of course, if I change this, you see it better. E, come on. E, O. Right, they're very different frequencies present. We could do some pretty amazing things by changing the shape of our mouth and changing the resonance in our mouths. And so that's how we change them. Now, with your instrument, you would look and you'd say, okay, my hypothesis is that my clarinet is a closed tube, and closed tubes should resonate at odd multiples of the fundamental. And so you play a note, you measure the frequencies, capture it, save it to put in your report, identify, does it match that? Does it actually have odd multiples of the fundamental? And as I said, one thing you can do is change. Notice my sound sensor frequency is changing depending on the pitch I'm doing. You can choose and change the frequency and get better resolution there, but I'm not going to go into that. That's the kind of thing you can do if you brought an instrument. If you didn't bring an instrument, then what you have to do is make your hypothesis something about the tube with the water and test your hypothesis doing something other than just the minimum of what you had to do. So it's actually a little easier if you brought the instrument because you can do your work there. So any questions? All right. Let's have a good